Hello everyone, today we'll present our project for computer networking course called Offline Traffic Analyzer. We are
Kecen Yao
Tianyu Liu
and Hongyu Yuan.
First of all, here's the overall structure of our project. The extractor folder contains the code for extracting different layers of the network packets. And the sample data folder contains the test files for the program. And the utils folder contains the utility functions used in the program, includes the data pre-processing functions. And the results folder is the default folder that contains the output files saved. And the network packet analyzer.py contains the main class for analyzing network packets. And main.py is the main file to run the program. Makefile contains the variables and the commands to run the program, and how-to.md contains the instructions to run the program. We choose this methodology is because 3 reasons. The first one, the scalability. Classes make it easier to scale our project. We can add new classes or extend existing ones without major modifications to our existing codebase. And maintainability, because classes segregate functionalities into well-defined interfaces, maintaining and updating the project becomes easier. It's clearer where changes need to be made, and the impact of these changes is often confined to a single class rather than rippling out the other parts of the project. And the improved debugging and testing. Classes often encapsulate behavior, making it easier to test individual parts of a project in isolation. This encapsulation helps in identifying bugs and issues more quickly, as we can focus on small, manageable sections of our project at a time. And the layer Ethernet is simple. The structure of Ethernet is what this graph shows. The first 6 bytes is the destination address, the next 6 bytes is the source address, then the next 2 bytes is the type. There are 3 different types. The hex value of 0806 is ARP, and the 0800 is IPv4, while 86DD stands for IPv6. For class IP implementation, we first check the version of the IP packet. If the version value is 4, then we use the parse header function to analyze the header, then use the parse options to analyze its frames options. If the version value is 6, we'll also use the parse header function to analyze the header. Since there's no option section in IPv6, there's no need to use the parse options function.
As for the UDP layer, it's relatively simple, so our class for the UDP layer simply parse through the header based on this header structure and pass the payload down to DNS layer or DHCP layer. For the DNS layer, our class decodes the 6 header fields and also the questions, answers, authority, and additional sections. It is able to decode all the information, including the compressed names, for which I will now explain in more detail. DNS compression is used to compress previously existed names to remove duplicates, and thus reduce the length of the DNS messages. This method targets all the names included in the 4 sections of DNS messages, which can be provided either as a sequence of data labels, as a compression label, or as a mix of data and compression labels. A data label starts with 1 byte, indicating the length in bytes of the label. The following bytes will be the value of the name. The new label 0x00 will follow after the last bytes of the name to indicate the end of the name. And a compression label refers to a 2-byte label which points to one or many consecutive data labels located above in the DNS message. A compression label is a 2 byte long. The value of the first 2 bits are set to 1, and the remaining 14 bits indicates the offset of the data labels to be reused in the DNS messages. For example, these screenshots are from a DNS response message displayed in Wireshark, which used name compression. The name google.com is firstly contained in queries, so the hex corresponding to this name use only data label representation. The first byte, 06, indicates the value of the first data label is 6 bytes long, and is translated as Google. The next data label value is 3 bytes long and translated as com. And the loon label 00 indicates the end of this name. When the second time the name google.com appears in the answer section, it is represented as a compression label C00C with the first 2 bits set to 1, indicating it is a compression label, and 14 bits to show the uncompressed name starts after the 12 bytes from the start of the DNS message. For the DHCP layer, our class can successfully analyze all the information contained in a DHCP message, as well as successfully decode the 8 types of messages contained in option 53. Now, let's watch a demonstration presented by Kecen.
Hello everyone, my name is Kecen, and here is the demonstration of our program. If you have cloned our repository in your local machines, you should see the following files in the left hand. And here, the how-to.mat files contains the detailed instructions on how to run the program. We have a very standardized input data file format. It should be a TXT file extracted from Wireshark, and it should be placed in the simple _ data folder. We have 2 ways to run our programs. The first way is to use makefiles to run the program. You have 4 variables to determine before you run the programs. The first one is the input file. It is the file that you want to do a single file analysis. The second one is the input files. It contains the multiple files that you want to analysis at the same time. The third variable is the saved result. If it is true, the result will be saved in a TXT file. And output folder is the destination folder of your result. If you use the makefile command, it will run the program on the one file specified in the input file. If you run the makefiles command, it will run the multiple files specified in the input files. Now let's do a demonstration. We can first input makefile in the command line. So this file contains more than 10 frames, so our program will display 10 frames at a time. You can press enter to see the next time frame, and you can see in the end the results are saved in results. And here are the detailed results of our file. Now let's take a look at the makefiles. If you use makefiles, every result will be output in the terminal, and they are also saved in the results folder. And you can check them in details. What's worth notice is that we also have a corner case handle mechanisms. If we encounter a package that we did not implement, we will have arrows indicate that. For example, if the package have protocol that have not been implemented, we will handle this error by saying in this case TCP protocol is not supported, but the upper layer protocol will be shown as normal. The second way to run our program is to use the Python command line inference. If you do not want